All right, welcome back to Math 160. We are moving right into chapter 5. We are going to start by talking about probability distributions. Fun stuff. It should be actually pretty straightforward, considering we do have an understanding of probability. So let's check it out. We're going to start with some definitions here. I know not the most fun thing, but no big deal. We're going to start by defining a random variable. So first off, typically when you see a random variable, its notation is going to be a capital X. Typically, you will see that random variable noted as a capital X. So a random variable, now this piece is very important. A random variable has a numerical single value. So has a numerical single value determined by chance for each outcome of an event. Okay. A random variable has a numerical single value determined by chance for each outcome of an event. We will see this we'll see all of this in just a moment. So when you think of random variables, I want you to think of some sort of experiment that takes on numerical outcomes, right? Numerical values. I'll show you what I mean. We have something called a probability distribution. This is really, really, really important. I want us to get comfortable with this terminology. So probability distribution. This is a description that gives the probability for each value of the random variable. I want you to think of this as a table, right? A table showcasing the probabilities of each outcome. One second. Be careful with the share screen, okay? Lastly, we have probability distribution requirements. So this is essentially talking about the fact that we know when we refer to probability, we know the fact that probability cannot be greater than 1 and it cannot be smaller than 0, right? We can't have negative probability and we can't have probability greater than 100%. So that's the first thing. One of the other components is that if we are truly representing a probability distribution, which takes into account all of our outcomes and all of their respective probabilities, then when we add those probabilities up, it should only add up to 1, right? Because 1 is total probability. Think of, for instance, flipping a coin. If you flipped a coin, the probability that it lands tails up is half, right? Or 0.5. The probability that it lands heads up is the same, half, 1 out of 2, or 0.5. When you add those two probabilities together, which are the only outcomes for flipping a coin, 0.5 plus 0.5 or 1/2 plus 1/2, we get 1, total probability. So keep that in mind as we move through these probability distributions. Those things have to be present. Let me write this down. The first requirement is that there must be a numerical random variable x and its values are associated with corresponding probabilities. Okay, there must be a numerical random variable x, and its values are associated with corresponding probabilities. The second piece is that the sum, remember that means sum where you add all your values up, the sum of your probabilities must equal 1. The sum of all probabilities must equal 1. That's super, super, super important. This is how you know you've taken into account all of your possible outcomes. And then number 3, we also have to keep in mind that probability, whatever your probability value is, must sit between 0 and 1 inclusive, right? Probability can take on any value between 0 and 1 and including 0 and 1. It's like me asking you, hey, what are the chances that you pick both a red and a black card, right? Like that you pick either a red or a black card. You would say, well, wait a second, any card I pick from a standard deck of cards will be either red or black. So that's 100% of the time. That's a probability of 1, right? 100% of the time, probability of 1. What if I then switched up my language and said, hey, what are the chances that you pick a card that is both red and black? You would say, not possible. That's simply not possible. So that is a probability of 0. And then, of course, your probabilities in between, right? What are the chances, for instance, that you pick a 10 from a standard deck of cards? You would say 4 out of 52. Right? There are 4 10s out of the 52 cards. If you plug that into your calculator, I can't even talk, calculator, you notice the value would be somewhere between a 0 and a 1. So kind of think about that. Always refer back to scenarios that you're familiar with. If you're not too familiar with cards just yet, because you will be, you got to teach someone a game or learn a game. If you're not too familiar with that right now, it's okay. You can always refer back to maybe rolling a die or flipping a coin. So other things that you are more accustomed to. Let's go ahead and flip the page here. All right, so probability distribution. We're going to start by looking at the probability distribution of tossing 2 coins, right? So when you think about tossing 2 coins, you want to consider the outcomes that you could have, right? You could flip the first coin, it's tails, the second coin is tails. The first coin is heads up, the second coin is tails up. The first coin is tails up, second one is heads up, or they can both be heads up, right? These are the different possibilities. These are the different outcomes. What we want to do is we want to call the number of tails up when tossing 2 coins the random variable. That's our x. So I'm actually going to highlight this statement. So we're saying let x be the number of tails up that you could get on 2 coins, right? So what that implies is that in this particular set of outcomes, we see that tails up can occur twice, once, or no times, 0 times. So x can take on any of these values. 0, 1, or 2. Remember, we're looking for the outcomes that have tails up. What we then want to do is we want to showcase the probabilities for each of these outcomes. So this reads the probability that a random variable is equal to 0, right? Let's rephrase this. The probability that the two coins show 0 tails is 1 out of 4. There are 4 combinations here. I'm going to make a note of that. There are 4 outcomes, right? The 4 outcomes are listed here for you. So the probability that no tails appears is 1 outcome out of the 4. This is the only outcome that has no tails up. For the second statement, this says, what is the probability that tails shows up once in the combination, right? In the toss of the 2 coins. Well, you'll see that we have heads, tails, tails, heads. So in 2 of the outcomes, 2 out of the 4, the number of tails is 1. So 2 out of 4, which reduces to 1/2. I'm going to just write that here so you know exactly where that 1/2 came from. The original probability was 2 out of 4. And then we say, well, what is the likelihood that when we toss these 2 coins, they both land tails up? And you would say, okay, well, one of those outcomes out of the 4 has the outcome of 2 tails up. So it's 1 out of 4. Are there any questions on this so far? This idea of rewriting it. So we have the probability that the random variable is equal to 0 tails, 1 tail, 2 tails. Okay.
I don't get it.
Okay, so you see how we have these 4 outcomes? And this is from tossing 2 coins, right? Do you agree that these are the only possibilities?
Yeah.
Okay, perfect. So we see that there are only 4 outcomes right here. What we're responsible for now is answering the question, what is the likelihood that when you toss those 2 coins, that you get 0 tails? So what we always like to do is we like to list what those outcomes are so that we could say, oh, well, 0 tails, that means that both coins land heads up. And only 1 out of the 4 will actually provide that. Does that part make sense?
Yeah.
Beautiful. Then for our second probability, we want to know how many outcomes has just 1 coin tails up. And then you say, oh, well, I've got 2 of them because this one doesn't count. This one has 2 tails up, so that one doesn't count. We just want the outcomes that have 1 tail. So heads, tails, that's our first outcome. Tails, heads, that's our second outcome. So it's 2 out of 4, which, by the way, we could have written as 2 out of 4, but we reduced it so that it's 1/2. Is that okay so far?
Yeah, I get it now.
Okay, perfect, perfect, perfect. I know sometimes this can definitely be a little bit tricky, especially the notation and the way in which we're describing this. So thank you for asking. I want to make sure that this is tight so that we can move on to more complicated problems. Now, the corresponding probability distribution would be the table below. So let's go ahead and highlight or underline probability distribution. Because remember, it's the table that identifies, the random variable values and their corresponding probabilities. So when we had up here, we just made a note that the likelihood that no tails would be seen on both of those coins is 1 out of 4. Notice 1 out of 4 is the same as 0.25. 1/4, 0.25. For the likelihood that 1 tails is seen in the tossing of both coins, that's going to be 1/2, 0.50, right? 1/2, 2 divided by 4, same thing. These both represent 0.50. And then finally, our last probability, 1 out of 4, same thing, 0.25. X represents our random variable. And in this case, it's the number of tails seen on the tossing of 2 coins. And then this P of X represents the probability of each outcome. Typically, you'll see these as decimals as opposed to fractions. So P of X is a probability of each outcome. I also want you to notice that if you take these probabilities and you sum them up, it will equal 1. I'm going to prove this to you. So 0.25 plus 0.50 plus 0.25, that's going to equal 1, which is exactly what we want. We want to ensure that our probabilities sum to a total of 1, which is total probability. So we've taken into account all of our possible outcomes. What questions do you have for me on the probability distribution? Okay, we're going to take a moment to construct a histogram based on this probability distribution. So let's go ahead and draw our, let me find my straight edge. That would actually be really nice. I have this Cheesecake Factory gift card that I've never used. I think I've had it for like, I don't know, years now. And I can't. Once you have Cheesy Eddies, how do you go to Cheesecake Factory? It's just not possible.
That is the best point of my life. Thank you for saying that. Cheesy Eddies is so good. I love it there.
It's
I
so
literally
amazing.
just finished a cupcake from Cheesy Eddies like 2 seconds ago.
Oh, I'm jealous.
And
My
you
cat
were-
got my freaking cheesecake.
And you were in heaven for the about 60 seconds it took to down that because it's too good.
Oh, 100%.
Exactly. Everyone, please check out Cheesy Eddies if you have not been there. Okay. So our vertical axis here, kind of, when you think about like your y-axis, this is going to represent our probability. So I'm going to go ahead and label that P of X. We're going to list our probabilities here, obviously in ascending order. So we're going to start with 0. And what I like to do is I like to try to space this out as evenly as possible. So I'm just going to start by putting my halfway point and then my maximum value. So my maximum probability is 1. My halfway point is 0.50. And now I'm going to mark the halfway points in between the lower and the upper halves, just so that I can try to make this as even as possible. Little strategies that tend to work. So we'll label this as 0.25 and our third marking as 0.75. So there's our vertical column listing our probabilities. Good. On our horizontal, I can't talk today, I'm struggling so hard. On our horizontal axis, our x-axis, we're going to call this the number of tails up, our random variable x, right? So I'm just going to label it as number of tails up. That's our x. And there were only 3 outcomes. It was either no tails, 1 tail, or 2 tails. Let me make my 1 a little clearer. Perfect. Remember, with histograms, there are no gaps in between the bars, so we want to make sure that these are connecting, and we also want to make sure that we represent each of these probabilities as accurately as we can. Obviously, we're drawing this by hand. So the likelihood that we have 0 tails up is 0.25. That's our probability. So I'm going to go ahead and I'm going to use just a dotted line to make my life a little bit easier. And then, of course, we'll shade this as our first bar. So the likelihood of 0 tails is 0.25. The likelihood of 1 tail is 0.5. So we're going to make sure that our second bar hits that probability of 0.5 as best we can. Remember, we're just doing this by hand, so we can only be as accurate as we're able to be without using software. And then, of course, 2 tails up is also 0.25. Let's finish this graph here. And voila, we have our histogram. This is a histogram based on the probability distribution. I will tell you, generally, you will not have to do anything like this, but it's nice to see the histogram based on that distribution, just so you can kind of get a sense of that visual. What is the shape of this distribution?
Bell-shaped.
A bell-shaped curve. Yes, beautiful. It's very normal, right? As opposed to skewed left or skewed right. Beautiful. Turn the page when you are ready. I would like to have someone else read this. So Nicholas, would you go ahead and read the first example under how do we determine if we actually have a probability distribution? Would you read that example?
Sure. In a 2020 global attitude survey conducted by the Pew Research Center, subjects were asked how well they thought the United States handled the COVID-19 outbreak among the 13 countries surveyed: Denmark, Japan, Spain, etc. The table below shows the results. Do you want me to read the table?
Sure.
Response: very, somewhat good. P of X 0.15, somewhat bad 0.31, very bad 0.53.
Perfect. Now take a look at this distribution table, this probability distribution. Is this an actual legitimate probability distribution? Let's talk about that. Let's talk about the requirements. So look back to page 6, part C. So it's the very first page on chapter 5, probability distributions. If you look back to page 6, part C, you'll notice that we have to have a numerical random variable. The sum of the probabilities must equal 1, and each of the probabilities must sit between 0 and 1. So take a look at our table. What are your thoughts when you look at those requirements?
It doesn't equal to 1?
Let's check it out. So let's try it out. So if you take this 0.15 plus 0.31 plus 0.53, what does that equal?
0.99.
Okay, so it does not equal 1. Now so when we think about something like this, we're pretty close. What this could be implying is that maybe there was rounding error. So I kind of feel like that's not quite enough to tell us that this is not a probability distribution. I mean, how many times have we completed a table and it didn't add up to that full value that we were looking for simply because of rounding error? So, I mean, that's pretty close, but I don't want to just throw it all away yet. What else do you notice?
The random variable doesn't have a numerical value.
Perfection. That's exactly correct. These are not numerical values. Very, somewhat good, that's not a number. Somewhat bad, that's not a number. Neither is very bad, right? These are the responses, but these do not take on numerical values. That would be different if we were provided with a Likert scale, right? On a scale from 0 to 5 or 1 to 5, what is your opinion on how the US handled the COVID-19 outbreak? Then you can have 1, 2, 3, 4, 5 as your responses on the Likert scale with their associated probabilities. In this case, it was not presented as such. So, does this table describe a probability distribution? No, because the responses are not numerical. You can also write that it would be different if, for instance, you used a Likert scale. I'll write that down. It could be if we used a Likert scale instead. So, on a scale of 1 to 5, for instance, right? On a scale of 1 to 5, what are your opinions of how the US handled the COVID-19 outbreak? 1 being, super terrible, and then 5 being extremely awesome. I'm being very informal, but you understand what I'm saying here. Beautiful. Okay, let's take a look at example B. So we have a particular function, p of x is equal to x squared plus 5 all over 50. Be careful with how you input this. And we're seeing that our random variable takes on the values 1, 2, 3, 4. Random variable takes on numeric values. Awesome. I love it. What we're going to do is fill in the table and then determine if it actually is a probability distribution. So let me show you what I mean by this. So for our first cell here, p of x is equal to x squared plus 5 over 50, keep in mind that we know what x is. X is going to take on the value of 1. So what I'm implying here is that to find the probability that your random variable takes on the value of 1, we're going to plug that into our formula. So we have 1 squared plus 5 over 50. So we have 1 squared, which is 1, plus 5 is 6. And so then our probability is 6 over 50. I'm not going to convert these into a decimal yet, only because I feel like we will end up with rounding error if we convert it to decimal form. So let's keep it in fraction form for now. Let's do the same thing with the second one. We want the probability that a random variable takes on the value 2. What's my fraction for p of x when
9 over 50.
9 over 50? Beautiful. Do the same thing for p of 3. What do you get it?
14 out of 50.
14 out of 50. Beautiful. And the last one?
21 out of 50.
21.
Yeah, 21 out of 50. Perfect. So the table is complete. Now we have to determine if this is truly a probability distribution. We know that our values took on our random variable took on numerical values. Check. We have to now determine if the sum of all the probabilities is 1. We do see that each of the probabilities sits between 0 and 1. So this is a success as well. So let's add these up, the sum of the probabilities, and let's see what we get. So we have 6 out of 50 plus 9 out of 50. You don't have to write all of this down if you don't want to. I just want you to see what I did. When you add all of these values, all of these fractions together, what do you get?
$50 out of 50.
Perfect. We get 50 out of 50, which equals 1. Success. It is, in fact, a probability distribution. This is.
So you keep the denominator the same, like you don't add the denominator.
Yes, you keep it the same only because you're combining fractions. Think about just addition and subtraction of fractions. You have to have a common denominator before you add or subtract. And now that they do have that common denominator, you can just combine the numerators, keeping that denominator. Excellent. Good. Very nice. Man, I feel like fractions is always the bane of our existence. And yet I love them so much. Beautiful. Any other questions on example B? Cool. Okay, on your own, take a look at example C. Given the following table, does this table describe a probability distribution? Please give a reason for your answer. explore this, look at our requirements and think about, is this a probability distribution? Don't say anything out loud, just take, maybe 60 seconds to decipher this. We see that the random variable does take on numerical values, so that part is a success. We see that each of the probabilities sit between 0 and 1, so that is also a success. But then we have to determine if the sum of the probabilities is equal to 1. Well, when we take 0.30 plus 0.26, right, that's 0.56 plus 0.10, that's only 0.66, which is not equal to 1. So no, this is not a probability distribution. We prove that it's not equal to 1 by showcasing the sum of those probabilities. Very nice. Excellent, excellent work so far. Okay. Now we want to calculate the mean and the variance of a discrete probability distribution. You remember how I mentioned maybe at one class at some point that it's going to be a good idea to have a sheet that contains all of your formulas. We're about to meet a couple formulas that should be on that sheet. You should label it mean and variance of the probability distribution, and then you should have the formulas right there, ready to go. That's going to be super helpful to you all. If you don't have that formula sheet created, I highly recommend you start that sheet today, okay? Think about doing that. You want to have a centralized location for all of your formulas, as opposed to going through each of your notes and trying to find what that formula is. Save yourself by using success strategies. This is one of them. It's another reason why, if we were meeting in person and taking tests in the classroom, you each would have a formula sheet with you. No joke. You'd come to take the test with a formula sheet with all those formulas written down. So I highly advise you to start that if you haven't done it yet. Okay, just a random sheet of paper. Label it formulas, you'll be good to go. All right. So first off, as a reminder, notice your notation for statistics and parameters. Statistics represent samples and parameters represent population. Remember, these are numerical values. As a reminder, X bar represents our what?
Mean.
Yeah, our mean. So this is a sample mean, which means mu is the population mean. What is S squared? Do you remember?
The variance.
Yes, this is the variance. Perfect. Which means sigma squared is also the variance, but obviously for a population. And then what is just S by itself?
Standard deviation.
Yeah, standard deviation. Love it. I'm just going to abbreviate because I can't quite fit it in there. Standard deviation. Standard deviation for a population is sigma. Very, very nice. As a reminder, we know that the variance is equal to the standard deviation squared, right? Right? And we know that the standard deviation is equal to the square root of variance. Couple quick formulas that you should definitely keep in your minds. Okay, the mean of the probability distribution of a discrete random variable, or the mean of a discrete random variable, is often referred to as its expected value. So the mean of the probability distribution is sometimes referred to as the expected value. The expected value is found quite simply by taking the actual random variable itself and then multiplying it by its probability. You do that for each random variable, right? Because you have a bunch of random variables. Like for our previous examples, let's look at, for instance, B. B is a probability distribution, so we're able to use this one. The random variable takes on the values 1, 2, 3, and 4. Each of these values takes on a different probability, right? So when the random variable is 1, its probability is 6 out of 50. When the random variable is 2, its probability is 9 out of 50. When the random variable is 3, its probability is 14 out of 50. And then when the random variable is 4, its probability is 21 out of 50. To find the mean or the expected value, what you do is you take each of those random variables and multiply them by their respective probabilities. Once you do that, you add all those up, and that'll give you the mean. All right, I think I'm going to show you this. I want to show you how we can calculate the mean for example B, just so that you get a sense of what's happening here. Okay, so we're going to calculate the mean, which is also known as the expected value. So you can see either phrase and know exactly what we're talking about. To find the mean, we are going to take each value of the random variable. So the first value is 1, and we're going to multiply it by its probability, which is 6 out of 50. So there's your first product. Then you're going to add to it the second product, which is the second value that the random variable takes on, multiplied by its probability. You're going to continue this pattern. So we have 3 times 14 out of 50. And then we have 4 times 21 out of 50. Any questions on this equation so far? How you just matched the random variable value and its probability. Multiply, 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 multiply. And then you add all of those up. So far, so good. All right, so let's actually do the math here. 1 times 6 out of 50 is 6 out of 50. 2 times 9 out of 50, remember, it's just numerator times numerator over denominator times denominator. This is 2 over 1. So that gives you 18 out of 50. If you're not comfortable with fractions, go ahead and write over 1, over 1, over 1, over 1 for each of those whole numbers. It's going to make it a lot easier to see that when you multiply, you just go left to right. 3 over 1 times 14 out of 50, that's going to give us 42 out of 50. And then 4 over 1 times 21 out of 50 is going to give us 84 out of 50. Those are our 4 products. Now to find the mean, all we have to do is add those 4 values up. So we add these 4 fractions. What does it give us?
150.
150 over 50.
Yeah, 150 out of 50. Do the math. What do we get?
3.
Perfect. So the mean, the average for this probability distribution is 3. Okay, that is our mean. That's our expected value. Any questions on the calculation?
How did you multiply the 18 and like the 42 and the 84 and the 150?
Oh, how you get that? Go ahead and place, and I'm going to do this in pencil. Go ahead and place each whole number over a 1, right? Because every whole number can be rewritten this way. And then remember that when you multiply fractions, you just go left to right. So you go numerator times numerator over denominator times denominator. So notice we have 1 times 6, which is 6, 1 times 50, which is 50. And you do the same thing for each one. 2 times 9 is 18, 1 times 50 is 50. Does that help?
Yeah.
Score. Beautiful. So you just go left to right. Very, very nice. Let's go back to our discussion on mean and variance. So we've calculated the mean for example B, just so that we can get a sense of what's happening and how to actually do this. The variance is definitely much more tricky, so I would recommend using a table to calculate the variance. And we're going to do this maybe once or twice by hand, but really we're going to use statistical software to calculate the variance. But I want to show you how you would do this for a probability distribution. So the variance, sigma squared, of a discrete random variable x is found by multiplying each possible value of the squared deviation from the mean by its own probability and then adding the products together. That is a huge mouthful. So this is a formula I want you to consider. This last one here, because this is going to help make everything really, really easy. What I was showcasing here is how we progress from our first line to our simplified line. So technically, using some mathematical properties, we can go from our first line to this final expression here. So the variance, right, of a discrete random variable. Remember, we're discussing probability distributions. So the discrete probability distribution is this formula here. Use this last one. This is going to make life so much easier if you use this last one. Now, I want to point out what this is saying. Take each of your random variables, the values, right, and square it. When you square each of those, you want to multiply each of them by their respective probabilities. And then you want to add all those up. So it's interesting how instead of just taking the random variable value and multiplying by its probability, you have to square it first before you multiply it by its probability. You add all those values up, and then that value, that final answer, you then subtract the mean squared. So you need to calculate the mean before you can use this formula for variance. So we do the sum, right? We add up all the products of the squared value and the probability of that particular value, and then you subtract the mean squared. Let's see this in action. I know that seems nuts. Just as a note, we know that the standard deviation is found by taking the square root of the variance. So it's just here again. I literally wrote in our notation exactly what I wrote here. The standard deviation is equal to the square root of the variance. So it's the same. You could even rewrite the standard deviation equals to the square root of the variance. It's the same thing. All right, let's actually check this out. Deloitte conducted a survey on connectivity and mobile trends in 2019 and asked US consumers ages 14 or older if they paid for increased home internet speed on any of their devices. The survey found that consumers either did not pay for increased home internet speed or they did on 1, 2, or 3 devices. The breakdown is shown in the table below. So we have the number of devices, and we have the frequency, right? We have the number of people, the number of consumers who said 0 devices, 1 device, 2 devices, 3 devices, etc. So we're going to start off by calculating the probability. We learned that to calculate probability, that's the same as identifying the relative frequency, right? So how would I find the probability, the likelihood that the consumer said they paid for 0 devices, that home internet speed, increased home internet speed on 0 devices? How would I calculate that?
Number of devices over frequency.
Ah, the frequency. Okay. So we figured that there's 0 devices, right? And that occurs 420 times. We want the likelihood of this particular occurrence. So what we actually want to do is we want to say, well, what is total frequency? So we're going to start by looking at how many people were surveyed essentially. So go ahead and take your calculators and find the total. We need this value.
$2,000.
Yes,
2,000.
so 2,000 people, 2,000 US consumers were surveyed. The probability that anyone would say that they increase their internet speed on 0 devices is going to be found by taking the frequency and dividing it by the total, right? Part over total. That's probability. Go ahead and punch this into your calculators, and I would like a decimal to the hundredths place, if need be. You may not even have to round.
0.21.
Perfect. 0.21. How about our second probability? 1 device. How would I write it as a fraction?
300 over 2,000.
Yeah, 300 over 2,000. Would you please provide the decimal?
0.15.
Excellent. Nicholas, very nice. Someone else. What about 2 devices? Good. Emma's correct. Holly's correct. Abby's correct. So you're saying 600 over 2,000 part over total. That leaves us with 0.3. I'm going to write it as 0.30 just so that we're consistent across the board. Angelica, perfect. And our last one, what is our decimal?
0.34.
Yeah, 0.34. So we have 680 over 2,000 is 0.34. So we've just found the relative frequencies. We've just found the probabilities, right? The likelihood that the consumer said 0 devices, 1 device, 2, and then 3. The next thing we're going to do is we want to multiply X, the random variable, the value of the random variable times the probability of X. So X times P of X. Here's X, here's P of X. X times P of X. 0 times 0.21.
0.
Yeah. The second one, 1 times 0.15 is 0.15. 2 times 0.30 gives us, yes, Emma, thank you, 0.60. And then 3 times 0.34.
$1.02.
Score. Now remember, before we even get an opportunity to calculate the variance, we have to find the mean. That's the first thing we're going to do. So in order to calculate the mean, recall, notice here, find the mean, variance, and standard deviation. In order to calculate the mean, we are going to add up the products of the value of the random variable and its respective probability. That means we're going to add up this column. Okay, to find the mean, we're going to add up this column here. So our mean is going to be equal to 0 plus 0.15 plus 0.60 plus 1.02. What is the mean for this probability distribution?
1.77.
Perfect, 1.77. We're going to keep this value handy because we need this in order to help us calculate the variance. Now, according to our formula for variance, we had to square each of our random variables before we multiplied it by its respective probability. So our first value is 0, so 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. You just square your value of the random variable. Now in this column, you want to take your x squared and then multiply it by its probability. So same thing, we want 0 times 0.21. That's going to give us a 0. Let's move to the next one. We have 1 times 0.15. That's going to give us 0.15. Now we have 4 times 0.30. Go ahead and write down that value. And then we are left with 9 times 0.34. And then go ahead and write down that value as well. Four times 0.30, you should have 1.2. And then 9 times 0.34, you should have 3.06. Underneath mu is equal to 1.77, I wrote mean. I'm also going to write expected value. I'm going to pause for a moment before we calculate the variance. What questions do you have for me? Okay, so to calculate variance, we're going to use this column here because our formula is as follows. If we want the variance, we have to add up all of the squared values of the mean multiplied by their respective probabilities, right? We have to add that up first. So this part of the formula is referring to adding up all the values in this column. But then after you add up all those values, you subtract the mean squared. Okay, let's do this. So because I have limited space here, I'm simply going to add up all these values in this column. So what is 0 plus 0.15 plus 1.2 plus 3.06? What's that going to give us when we add these values up?
4.41.
Yes, 4.41. We're then going to subtract the mean squared. We calculated the mean. The mean is 1.77. If it helps, what I'm going to do is I'm going to do this piecemeal. So we have 4.41. If you square 1.77, you should get 3.1329. And then, of course, we subtract. So what is our variance? Yes, thank you, Angelica. 1.2771. There is our variance. Beautiful. And finally, how do I calculate the standard deviation again?
Square root the variance.
Done. So the standard deviation we know is found by taking the square root of the variance. Would you please provide the standard deviation to me to 2 places after the decimal? When you take the square root.
1.13.
Yes, perfect. Thank you, Kelly. Thank you, Angelica. 1.13 is correct. So here we have each of the three values, our mean, which is our expected value, our variance, and then our standard deviation. What I'm going to do now on the next page is I'm going to interpret what that means, because it's fine and dandy that we can calculate it, but what in the hell does that mean? So I'm actually going to write a statement that kind of puts all of these things together. So let's turn the page. You're going to need this info though. So you're going to turn the page to part B. Notice it says explain what the values of the mean, variance, and standard deviation represent with respect to the number of devices that used increased internet speeds in a household. So here's a statement, a very succinct statement that combines all of those. So you can note, on average, we can expect. Notice the terminology that I used, expect. We know that expected value is the same as the mean. If we turn to the previous page, the expected value is 1.77, but what does that mean? It means the following. On average, we can expect 1.77 devices, right? Because we're referring to the number of devices that has increased internet speed. We can expect 1.77 devices to have increased internet speed with a variance of 1.2771 devices and a standard deviation of 1.13 devices. Remember, standard deviations represents the spread of the data, how far you are from the mean. I want you to think back to that normal curve. And as a matter of fact, we're going to use that for part C. On average, we can expect 1.77 devices to have increased internet speed with a variance of 1.2771 devices and a standard deviation of 1.13 devices. Let's take it a step further so we can understand what the heck we are kind of referring to when we talk about usual values. So determine what the maximum and minimum limits are for usual values and what they represent. When you hear this phrase, maximum and minimum limits for usual values, you must think range rule of thumb. Does anyone remember how we calculate the min and the max for the range rule of thumb? How do you calculate it? Yes, Angelica, damn, you are on it. I know who's acing their first test. I know this with a certainty. Angelica's right. To calculate the minimum, you are going to take your mean and subtract 2 times the standard deviation. To calculate your maximum, you're going to take that same mean and you're going to add 2 times the standard deviation. That's your range of values. So from our previous page, our mean was 1.77. And our standard deviation was 1.13. So we're just going to apply the formula here. To find the minimum usual value, take the mean, subtract twice the standard deviation. To find the max, take the mean and then add twice the standard deviation. Please punch this into your calculators and would you provide to us the minimum value? What do you get when you punch this in? Emma, thank you so much. negative 0.49. It's definitely a negative. Be very careful with that. It is a negative 0.49. What about your maximum? You can send that to me privately. Thank you, Mike. Ava, thank you. So you're saying the maximum value, Nick, thank you so much, is 4.03. Thank you, Abby. Thank you, Leah. Good. So I'm going to write a statement that explains what this means. This means it would be usual to find that internet speeds are boosted for 0. You can't have negative devices, so this negative 0.49 is outside of 0, so we can include 0 in our range. Internet speeds are boosted for 0 to 4 devices. Your range runs from negative 0.49 to 4.03. So when you think of these as your bounds, notice the next whole number greater than a negative 0.49 is 0, of course. And the whole number that is smaller than 4.03 is 4. So it would be usual to find that internet speeds are boosted for 0 to 4 devices. That would be usual. It would be unusual if internet speeds were boosted for 5 devices, anything outside of that. And we can't go lower than 0, so that's our minimum. What questions do you have for me? That was a lot. I know it was a lot, but you did it. We got through it. It was very methodical. Keep in mind that as you work on problems, you want to do the same thing. You want to move through this very methodically. You want to make sure you have everything organized, clearly laid out, which means you may just need extra space on sheets of paper to write anything down. Just be really, really careful with all of your calculations. Okay? Perfect. I will send you all a recap of what we have accomplished and a reminder for all the assignments that are coming up. All right. So make sure you're focused on that. If you would like, you can start playing around in Unit 5. It's not necessary, but it's an option if you do finish your other work. All right. Good luck, everyone. I will see you all on Monday.
Thank you.
You're welcome.